Hello guys, today in this video we are going to discuss about the Block theorem and the Kronig Penney model. So let us see what is the Block theorem. The one-dimensional Schrodinger equation for an electron moving in a constant potential, okay, V naught, for example, V naught is the constant potential. We can write the one-dimensional Schrodinger equation for the electron moving in this potential V naught as d square psi by dx square plus 2m by h bar square e minus v naught psi equals 0. So the solution to this differential equation are plane waves, and the plane waves can be written in the form psi of x, one dimension, e to the power plus minus I kx. So this can be written as the solution of the above differential equation. And this e minus v0, where this e minus v0 is actually given by h bar square k square divided by 2m. Okay, h bar square k square is nothing but p, the momentum, so p square divided by 2m, okay, which is nothing but the kinetic energy. Okay, so for an electron moving in one-dimensional periodic potential Vx, the Schrodinger equation can be written as d square psi upon dx square plus 2m by h bar square e minus px psi equals 0. So this can be written for the Schrodinger equation for the electron moving in a potential which is a function of x. Now, since the potential is periodic, okay, since the potential is periodic, with the periodicity is equal to the lattice constant, okay, with lattice constant a, we can write, the potential will be repeated after an interval of x plus a. So okay, we said the potential is periodic and the periodicity or with period equal to the lattice constant a, right? There is an important theorem known as Block theorem which we are discussing, or also known as the Floquet's theorem, Floquet, Floquet's theorem, or known as Block theorem, which is actually concerned with the solution to the wave equation. This particular wave equation, d square psi by dx square plus 2m by h bar square e minus v of x psi. This vx is a periodic function here given by what? Vx equals to vx plus a. That means the potential will be repeated after interval of a, where a is the lattice constant. So according to the Bloch theorem, the solution to this equation are plane waves, and the type of the plane wave we can define as psi of x equals to e to the power plus minus I kx, which are modulated by a function ukx, we wrote, having the same periodicity as that of the lattice. That means what? This uk will be repeated after a periodicity of lattice constant. So the solution can be written as, the wave function can now be written as e to the power plus minus I kx ukx. Okay, and what is that ukx? Ukx is also a periodic function given by what? Ukx will be exactly the same after an interval of a, that is the lattice constant. Okay, so this wave functions, the psi of x is equal to e to the power plus minus I kx ukx, okay, are known as Bloch functions. Okay, now let us discuss about the Kronig Penney model. So what is this Kronig Penney model? So here we were discussing about the movement of electron inside the lattice in a crystal structure, where it will experience a periodic potential. So that periodic potential we have already discussed this way because of the periodic arrangement of the atoms. We said, these are the periodic arrangement of atoms. Then electron will experience potential like this, which is kind of periodic. We got periodic potentials. Okay, so periodic potentials like this. So here this model can be um, so for mathematical simplicity, we can rewrite, remodel this, okay, where, the potential can be taken as a periodic function, okay, and it will be repeated after the interval of the lattice constant. Then we can see what are the result or outcome we are going to get from this model. Okay, so let us, take this model to be series of potential well separated by, potential barriers like this. Okay, of course, identical. I mean, to say this is, suppose I will write minus B and this is 0 and this is A. So you can see the potential, suppose, is across this is our potential we have measured, right? And two regions I have shown. Region 1, where the potential I will consider to be V0, that is, here you can see the V0 constant potential, and here in region 2, where we got the potential to V0, V of x is equal to 0, right? So this way we can think of the potential, varying from a minimum value to a maximum value after a certain interval. Okay, so after a certain interval of a plus b, you can see, so the same value will be repeated after interval of a plus b, right here. So this is what is, for example, this is our x, okay, the distance, and here the potential as a function of x, right? So this is a one-dimensional periodic potential we are going to use in the Kronig Penney model. Okay, this particular model actually illustrates the behavior of electrons in a periodic potential by assuming a relatively simple one-dimensional model of periodic potential. So here we consider one-dimensional, relatively simple model where we consider the potential is only a function of x. So we are considering the one-dimensional model. Now the potential energy of an electron in a linear array of positive nuclei is assumed to have the form of a periodic array of square wells. Okay, series of wells you can see here. Okay, series of wells with period of a plus b. That's what we considered here in this mathematical model. At the bottom of a well, where we consider, the x value lies between 0 and a. Okay, x value lies between 0 and a. The electron is assumed to be in the vicinity of a nucleus, and the potential energy is taken to be 0. So v of x we considered is 0. Whereas outside a well, okay, for example here minus b to 0, where we wrote x is less than 0 and greater than minus b, the potential is assumed to be some value v0, a constant value v0, right? So let us write for these two regions, region 1 where Vx is V0, region 2 where Vx is the potential energy is 0, right? Let us write the Schrodinger's equation for these two regions. So if you'll write for V is equal to 0, that is the second region, for V is equal to 0, if you write the Schrodinger's equation can be written as d square psi upon dx square plus 2m by h bar square and e minus v. So v is 0 here, so e psi equals 0. This is what we can write. for v is equal to 0. Similarly, for v is equal to v0, the other region, that is the region 1, this was for region 2, and for region 1, similarly for v equals to v0, we can write d square psi by dx square plus 2m by h bar square e minus v0. Now we consider v is v0, psi equals to 0. That is applicable or valid for x lying between minus b and 0. Minus b and 0. Okay. So these are the two Schrodinger's equations we can write for these two regions where the potential is 0 and the potential is v0 respectively, right? So now assuming that the energy of the electrons is less than v0, okay, let us define two quantities. So we will define this way. So let me just rewrite the equations. Schrodinger's equation, d square psi by dx square plus 2m by h bar square e psi is equal to 0. This is for v is equal to 0 and x being between 0 and a. The other one, d square psi by dx square plus 2m by h bar square and e minus v equals to v0, psi equals 0. This is for v equals to v0 and x lying between 0 and minus b, right? Okay, so what we said, assuming that the energy of the electrons is less than v0, we will define two real quantities alpha and beta in such a way that alpha, suppose I will write alpha square is given by 2me divided by h bar square, right? So for this 2me by h bar square, and let us take beta square. These are two real quantities we are considering. So 2m, and let us take this as v0 minus e, okay, divided by h bar square. So here if I'll substitute, here you can substitute alpha square, and 2m by h bar square e minus v0 by h bar square is here, but here we consider v0 minus e, so we can substitute minus beta square here for this, right? So substituting these values of alpha square as 2me by h bar square and beta square as 2m v0 minus e by h bar square, and rewriting the equation, okay, what we can write is d square psi by dx square plus alpha square psi equals to 0. This is for x lying between a and 0. The other equation, d square psi by dx square, and then we consider minus beta square psi is equal to 0. Here x lies between 0 and minus b, okay. Now, what we have considered already, the potential is periodic. So the wave function must be of the form of Bloch function. Okay, Bloch function already we have discussed. So the wave function, as the potential is periodic here, it will be repeated after interval of a plus b as per the model that we have considered. So we can write psi of x is equal to e to the power I kx ukx is the periodic function, okay, with periodicity of a plus b, this is the periodicity of this Bloch function ukx. Okay, now what we can write, if it is it will be repeated after interval of a plus b, that means we can write uk function of x is equal to same as that of x plus a plus b, as it is a periodic function and it's considered to be a Bloch function. So this way we can write, okay, so ukx plus a plus b. Now let us find out d psi by dx and d square psi by dx square, and let's see what we are getting from this. We got the assumed solution here, psi of x is equal to e to the power ikx ukx, right? So if I'll write from there, d psi by dx will be ik e to the power ikx ukx. So the first function plus keeping e to the power ikx constant, and then duk by dx. Okay, then taking the second derivative, d square psi upon dx square will give us minus k square e to the power ikx ukx plus the second term 2ik e to the power ikx duk by dx plus e to the power ikx d square uk and dx square. Okay, so this is what we got for d square psi upon dx square and d psi by dx. So now if we'll substitute in the first equation, Schrodinger equation, the first Schrodinger equation we wrote was d square psi upon dx square plus alpha square psi is equal to 0. Now if we'll substitute these values, what we can write is d square, okay, for one function, let me write it the uk value as u1. Okay, so d square u1 upon dx square plus 2ik du1 dx plus alpha square minus k square u1 is equal to 0, right? So this is the first one we got. This is applicable for x lying between a and 0, right? So the first Schrodinger equation we got like this. Now similarly, the second one we can write, and the function, instead of u1, I will write u2 just to distinguish another function, Block function, which is valid for the second Schrodinger equation that we have considered. So let me just write that way, exactly the same way, and we'll substitute in the second equation. So we can just write it repeatedly the same thing, d square u2 upon dx square plus 2ik du2 by dx. Now in the beta equation, we got minus beta square plus k square k u2 is equal to 0, right? This is valid for x lying between 0 and minus b. The same way we need to do. So I just wrote it directly. Okay, so u1 and u2, okay, these are the values of ukx, right? In the interval of different intervals we have considered. U1 we considered when x lies between 0 and a, that is for u1, right? And when we considered x lies between 0 and minus b, we considered the Block function to be u2. So that is what we have considered. So now u1 can be written as the solution for these differential equations by solving this, or writing the general solutions only. Write the general solutions: a to the power I alpha minus k times x plus b e to the power minus alpha plus k times x, right? So these a, b are constants which can be determined using the boundary conditions. We will see it later. So okay, this is valid for x lying between a and 0. Okay, this solution we got. Similarly, u2, the general solution, can be written as c e to the power, this is beta minus ik times x plus d times e to the power minus beta plus ik times x, okay, x lying between 0 and minus b. So you got u1 and u2, the Block functions, right? And if you want to find out the the constants like a, b, c, d, these random constants we have used, it can be determined from the boundary conditions. Okay, so what are the boundary conditions we can write? Okay, so u1 at 0 must be equal to u2 at 0. Then du1 by dx, okay, at x equals to 0 must be equal to du2 by dx at x equals 0. Okay, similarly, substitute at x equals to, so is at 0x0, u1 is equal to u2, and at x equals to 0, their first derivative is also equal. Similarly, as we have already discussed the periodicity, u1 at A will be u2 at minus B. Okay, x equals to minus B. And you can also write du1 by dx at x equals to A must be equal to du2 by dx at x equals minus B, right? So these are the boundary conditions which can be used. From the diagram it is evident these values. Okay, so from these boundary conditions we can obtain four linear homogeneous equations. So these boundary conditions, you can see 1 2 3 4 four equations can be obtained, right? So you substituting in the first one, we can write it like, we have already obtained a plus b, u1 and u2 in terms of a b, u2 in terms of cd, u1 in terms of a b. So just substitute these values, like substitute x equals to 0, and here for the second side x equals to a for u1 and x equals to minus b for u2. Similarly, this set of equations here, first derivative at x equals to 0, okay, of u1, first derivative of u2 at x equals to 0, at x equals to a, and then at x equals to minus b. It will give us four homogeneous equations. So the first condition will give us a plus b equals c plus d if we'll substitute in the general solution that we have already written. The second set of equation gives us ai times alpha minus k minus b times I alpha plus k, that equals c times beta minus ik minus d times beta plus ik. Okay. Similarly, the third one we can write e to the power I alpha minus k times a plus b times minus I alpha plus k times a must be equal to c times e to the power minus beta minus ik times b plus d e to the power beta plus ik times b. Third equation, 1 2 3 by substituting. And the fourth one, similarly taking this one, the derivative, okay, we can rewrite it using the eraser. So we can write the last equation that can be obtained, ai alpha minus k e to the power I alpha minus k times a minus b times I alpha plus k e to the power minus I alpha plus k times a is equal to c times beta minus ik e to the power minus beta minus ik times b minus d times I beta plus ik e to the power beta plus ik times b. Okay, so fourth equation, this is the fourth equation, 1 2 3 and 4. Okay, these four equations we obtained using the boundary conditions, right? Now these equations can be used to determine the constants a b c d. Okay, those constants we have taken for u1 and u2. A non-zero solution to this equation exists only if, okay, only if the determinant of the coefficients of a b c d that we have written will be 0, right? So the coefficients here, as you can see here, 1 1 1 1, the coefficients of a b c d. Similarly here you can see the coefficients, right? So the determinant of the coefficients will be 0, then only it will have a non-zero solution. Okay, so let us write all these coefficients in a determinant form. So we will arrange it in a determinant form. The first one, first coefficients of a, let us write and put it in the determinant form. I times alpha minus k e to the power I times alpha minus k a, I times alpha minus k e to the power I alpha minus k times a. right? Then B, the coefficients 1 minus I alpha plus K e to the power minus I alpha plus K times A minus I alpha plus K e to the power I alpha plus K times A. Then C1 beta minus Ik e to the power minus beta e to the power beta minus Ik times A, and last one beta minus Ik e to the power minus beta minus Ik times B. Okay, and the coefficient of D1 minus beta plus Ik, okay, and e to the power beta plus Ik times B, the last one minus beta plus Ik minus outside e to the power beta multiplied, of course, beta plus Ik times B, right? So the coefficients of A here, B, C, and D taken in the determinant form. If this determinant will be 0, then only we will have a non-zero solution, okay, to these equations. So now on solving this equation, this solution will be little complicated. I'm avoiding that, okay, exactly opening the determinant, but directly I'm jumping to the the final solution, okay, or the equation. So if we will solve it, finally we can get this, okay, in the form of beta square plus alpha square divided by 2 beta alpha sine hyperbolic beta b sine alpha a sine hyperbolic beta b, okay, and sine alpha a plus cos hyperbolic beta b cos alpha a, okay, that must be equal to cos K times A plus B. So on solving that determinant, we will get this final equation. Okay. So now what this equation actually will give us, okay, this equation will actually, the motion of an electron in a periodic potential. Okay, using that equation, we got this. And using this, we can actually get for these results, okay, what it can give us. The first conclusion that we can make studying this, which we will do in some other video, we can show that there exist only certain allowed energy bands. Okay, so allowed energy bands, it talks about allowed energy bands, okay, separated by forbidden regions or band gaps, we call it. Okay, so this particular equation, if you'll study it, it will give us information about the allowed energy bands separated by forbidden regions, okay, or band gaps separated by forbidden regions, forbidden energy regions, of course, regions, or we call those band gaps, okay, which we'll study. So studying this equation, we can obtain this, okay, information about allowed energy band and the band gap. The second thing that it can give us, the energy function, okay, the energy function, okay, E as a function of K, okay, is periodic, okay, so it's a function of K, which is the wave vector. So energy is a function of K, which is wave vector, which is considered to be the wave vector, and here it is periodic. Okay, energy function is a periodic function. Okay, for the free electron theory, in the free electron theory, we have already obtained that E is equal to h bar square K square by 2m, considering the potential to be 0, right? So there is no upper limit to the energy, and K can have discrete values, which means that the energy levels are discrete. okay, and may have any spacing depending on the dimensions of the box. So that is what we are going to study. And the existence of band gaps is the most important property, okay, which emerges when the free electron model is extended, okay, to include the effect of periodic potential of ion cores. So initially, that's the failure of free electron model, and from that we started this band theory of solids. And in band theory of solids, we considered this Kronig Penney model, where we consider a simpler mathematical model, and we said what will happen if the potential function is a periodic one. Then we wrote the Schrodinger equation. From the Schrodinger equation, we use the Block theorem and used a Block function, which will be a periodic function, and we substituted that. And from this, we got a final equation, this equation. And we will, in the next video, we are going to study this equation and what can be obtained from this equation. This equation is this. Okay, there are discrete values of energy, and there are certain allowed energy bands, okay, and separated by forbidden regions or the band gap. Okay, so we will continue in the next class. Thank you.